For centuries, astronomy was a visual science. We explored the cosmos by observing light, from the twinkling of stars to the glow of distant galaxies. But in 2015, something changed. For the first time in human history, we heard the universe. It wasn't a sound in the air, but a ripple in the fabric of reality itself, a disturbance in space-time. This was the discovery of gravitational waves, and it marked the beginning of a new era in astrophysics. Let's explore what gravitational waves are, how we detected them, and what they're revealing about the dark, violent symphony of the cosmos. What are gravitational waves? Gravitational waves are ripples in space-time caused by the acceleration of massive objects. Think of space as a flexible sheet. If you drop a bowling ball onto it, it creates a dimple. That's gravity. Now imagine two massive balls orbiting each other. Their motion sends waves rippling across the sheet. These ripples travel outward at the speed of light, stretching and squeezing space itself. Albert Einstein predicted their existence in 1916 as part of his general theory of relativity, but he believed they'd be too faint to ever detect. He underestimated human determination. Where do gravitational waves come from? Only the most extreme events in the universe generate gravitational waves strong enough for us to detect. Merging black holes. Two black holes spiraling into each other generate massive gravitational waves in their final seconds before collision. Neutron star collisions. When two neutron stars merge, they emit gravitational waves, and often light, gamma rays, and heavy elements like gold. Supernovae. The explosive death of a massive star can send shockwaves through space-time. The early universe. Some theories predict that primordial gravitational waves were created just after the Big Bang, echoing across space-time. These cosmic events are among the most energetic and mysterious phenomena known, and gravitational waves let us hear them across the void. How do we detect them? Gravitational waves stretch and compress space by less than the width of a proton. To detect something so small, scientists built one of the most precise instruments ever made. LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO has two arms, each 4 kilometers long. A laser beam is split and sent down each arm. If a gravitational wave passes through Earth, it slightly changes the length of one arm compared to the other, producing an interference pattern in the laser. It's like detecting a change the size of an atom over 4 kilometers. The first detection came on September 14, 2015. A faint, rising chirp. It was the death cry of two black holes merging 1.3 billion light-years away. Since then, LIGO and its European partner Virgo have detected dozens of gravitational wave events, and the list is growing. Why gravitational waves matter. This is more than just a new way of observing space. Gravitational waves are a revolution. They allow us to see the invisible. Black holes don't emit light, but when they merge, they scream in gravitational waves. Test relativity. Every wave we detect confirms or challenges Einstein's predictions. Measure cosmic distances. Like cosmic sonar, gravitational waves help us map space. Study extreme matter. Neutron stars are the densest matter in the universe. Their collisions teach us about physics beyond Earth. Explore cosmic origins. Primordial waves could reveal secrets about the Big Bang, inflation, and quantum gravity. It's like discovering a whole new sense. For the first time, we're not just seeing the universe. We're listening to it. The music of the cosmos. Gravitational waves don't produce sound in space, but when converted into audio frequencies, they can be heard. And they sound astonishing. The first signal, GW15914, resembled a chirping bird, rising in pitch and frequency until it suddenly stopped. That was the moment two black holes collided. Other detections sound like drum beats, hums, or ringing tones, depending on the mass, spin, and speed of the merging objects. Each waveform is unique, a signature of a cosmic event billions of years ago. It's like discovering the soundtrack of the universe. Multi-messenger astronomy. One of the most groundbreaking detections came in 2017. A neutron star merger called GW 170817. For the first time, gravitational waves and light were detected from the same event. Astronomers observed gravitational waves, gamma rays, optical light, X-rays, and even radio waves, all from a single cosmic collision. This ushered in multi-messenger astronomy, where we observe the universe with multiple signals, not just light. It's as if the universe went from silent film to full surround sound. The future of gravitational wave astronomy. We're just getting started. Future detectors will take us even deeper. LISA, the Laser Interferometer Space Antenna, will launch in the 2030s. It will detect lower frequency waves from supermassive black hole mergers across the universe. Einstein Telescope, a proposed underground European detector with 10x the sensitivity of LIGO. Cosmic Explorer, a next-generation U.S. observatory to probe early universe signals. We may even detect primordial gravitational waves, the faint echoes of the Big Bang itself. And with more data, we could discover new physics, extra dimensions, exotic particles, or changes in gravity over time. Final thought, gravitational waves have opened a new sense, a way to hear the deepest movements of the universe. They come from cataclysms, collisions, and creation itself, and they carry messages that light can't deliver. In every ripple, we find not just evidence of the past, but proof that the universe is alive with motion, drama, and music. Here on Infinity Beyond, we listen closely, because the universe is speaking, and its voice is beautiful.